is if those two functions are some constant. So we have f of xy is equal to x squared y plus some constant c. Okay, so then this later on we'll see would be something like the internal energy depending on temperature and enthalpy, for example. Okay, so you would end up with something like this. Okay, any questions on this? Okay, let's have a look at the next one. That's 2.2. Okay, so the other differential that was exact, that was the x dx plus y dy. It was that differential. So we want to do the same thing. We're going to have df by dx being equal to x. So this means that f of xy is equal to the integral of x dx plus some function of y. So that means f of xy is going to be 1/2 x squared plus some function of y. Okay, we can do the same for the other part. df by dy is equal to y. So that means f of xy is going to be the integral of y with respect to y plus some function of x. So f of xy is equal to 1/2 y squared plus some function of x. Okay, now if we compare both expressions for f, we see that our final answer, f of xy, must therefore be 1/2 x squared plus 1/2 y squared plus some constant c. Okay, so that would be one of our thermodynamic potentials. Okay, any questions on this one? Okay, let's have a look.
So these type of maths we're going to properly use like after the second law, so not during the first law, or
no, both. So it's with the first, because remember the first law, that was the du is equal to dq minus p dv. Remember that?
Yes, sir.
Yep, that's exactly what we've got here. So then this would be something like df is equal to df by dx dx plus df by dy dy. So instead of f, we have u. So that's our f. And then we've got dq, that's like our dx. And we've got dv, that's like our dy. So we see that the partial derivative of u with respect to v would then be minus p in this case, because we know that du is exact. So from here we can see du by dv is minus p, for example. Okay, so we're already using it now, but then we will be using it again later on when we look at thermodynamic potentials. Okay, but already you can see where this is being used. We know that du is exact, so it must satisfy this expression here. However, we can't do that for dq because that's inexact. So we can't do this. Okay. Any other questions on this? Okay, let's have a look at question 3. So this was doing the line integrals. So 3.1, we had the integral of 2xy dx plus x squared dy. Okay, and we were given the following curve gamma. It was y equals x, where x goes between 0 and 1. Okay, so we want to calculate this integral. So we've already got a parameterization of it in terms of x. So we can write this as the integral from 0 to 1, 2x times x plus x squared, put all of that in brackets, dx. Okay, so this will be the integral from 0 to 1, 2x squared plus x squared, so that's going to be 3x squared dx. And then this will be x cubed from 0 to 1, so that's just going to be 1. Okay, so this is something that you would be doing when calculating the work done or calculating the total amount of heat transferred. You'd have to integrate some kind of differential. Okay, so that's 3.1. So this is using the straight line path. The other option was using the parabola. And we know that since this is an exact differential, we should get the same answer. So let's do it the other way. So we have the integral 2xy dx plus x squared dy. Now we're taking the parabolic path, y equals x squared, 0 less than x less than 1. So here we see dy is going to be 2x dx. So this will be the integral from 0 to 1, 2x times x squared plus x squared times 2x dx. Okay, so that's the integral from 0 to 1. 2x cubed plus 2x cubed, so that's going to be 4x cubed dx. Okay, that will be x to the 4 from 0 to 1, and that's just 1. Okay, as expected, because we know that this is exact, so both paths should give us the same answer. Okay, and if we were to find the function for this and then evaluate, so the function that gives us this differential, so the f such that df equals 2xy dx plus x squared dy. If we find this function and evaluate it between the endpoints, we should also get 1. Okay, so yeah, that's because this is exact. So if you know the function, we just need to evaluate it at the endpoints and we get our answer. Or if you take any path between the endpoints, we should also get the same answer. Okay, any questions on this? Okay, so this is in terms of X and Y, but your test problems and tutorial problems and so on, that would be finding, for example, the total work done. You have to integrate the differential, the total heat transferred, the total energy, etc., along some process curve. Okay, but the method is exactly the same as this. Okay, let's look at 3.2, which is an inexact differential, and we should see that it is path dependent. Okay, and in that case, you would put that line through the D there. Okay, so 3.2. We have the integral of x squared dx plus x cubed y dy. Okay, and we want to take those two paths. So the first one, okay, that's y equals x from 0 to 1, and see what we get. This is going to be the integral from 0 to 1, x squared plus x to the 4 dx. Okay, so that's going to be 1/3 x cubed plus 1/5 x to the 5 from 0 to 1. So that's 1/3 plus 1/5. So that's 8/15. Okay, so that's for the first path. Now we know that this is inexact. So for the second path, we should get a different answer. Let's check that. So we want the integral of x squared dx plus x cubed dy. Sorry, x cubed y dy. It's an extra y there. Okay, but now along that parabolic path, y equals x squared from 0 to 1. Okay, so what do we get in this case? So this will be the integral from 0 to 1, x squared plus x cubed times x squared, and then dy is going to give us 2x dx. Okay, so that will be the integral from 0 to 1, x squared, plus we're going to have 2x to the 6 dx. Okay, integrating this, we're going to get 1/3 x cubed plus 2/7 x to the 7 from 0 to 1. That's going to be 1/3 plus 2/7. So that's going to be 13/21. Okay, and as expected, we get a different answer because we took a different path. Okay, so this kind of differential would be something like heat. Okay, you do a different path. So since it's inexact, you do a different path, you get a different value. And in some situations, remember, work done is also inexact. So if you take a different path, you can get a different value. Okay, any questions on this example? Okay, let's have a look at the next bits, homework 2. Okay, so this was finding the work done for several types of processes. Remember, we categorized them isochoric, isobaric, isothermal, adiabatic. We gave them all those different names. So the first one was isochoric. So remember what isochoric means. That means V is constant. Okay, so if we're doing an isochoric process from V1 to V2, we know that V1 is equal to V2. We can just call it V. So how do we find the work done? The work done is the integral from V1 to V2 of P dV. That was our differential for work, P dV. This is equal to the integral from V to V of P dV, because it's isochoric. The lower bound and the upper bound are the same. So this just gives us 0. Okay, so the work done in an isochoric process is going to be 0. The second question was isobaric. So for an isobaric process, we know that P is constant. Okay, so with that in mind, what's the work done? So W is going to be the integral from V1 to V2, P dV. This is always your starting point. Okay, so whenever you're finding the work done, you always start with this, and then you see what can I do from there. Maybe your dV needs to change. Maybe P is some function of V. You put all of that afterwards and you see what you get. But what's in the red box, that's always your starting point. Okay, and this is the work done by the gas. So it's the pressure of the gas pushing it outwards. If you want the work done by the environment, remember you put that minus sign. Okay, this is going to be, well, P is a constant, so we can just take that out of the integral. So it's going to be P integral from V1 to V2 dV, but that's just going to be P times V2 minus V1. Okay, so that's for an isobaric process. Next is an isothermal process. Isothermal, so that implies that T is constant. Again, we have exactly the same starting point. W is the integral from V1 to V2, P dV. But now in this case, P is not constant, T is constant. So we need to find a function P in terms of V so that we can integrate. So we do that using the equation of state. So typically we work with ideal gases, not always. You'll see in hand-in problem number 2, it's not an ideal gas, but you follow the same procedure. But let's just say this is an ideal gas. So we have PV equals nRT. T is constant. We can solve for P. So it's going to be nRT over V. So this is our function of V. Let's just write that explicitly. P as a function of V. Okay, so let's substitute that. So this will be the integral from V1 to V2, nRT over V dV. The nRT, those are constants, we can take that out. So that's going to be nRT, integral from V1 to V2, 1 over V dV. That's easy enough to do. That's going to be the natural log. So this will be nRT, the natural log absolute value V2 minus natural log absolute value of V1. So remember, whenever you're integrating 1 over x, it's the natural log with an absolute value. Now we know physically that volume cannot be negative. So in the next step, we can drop it if you want to, or you can leave it there. It makes no difference. Okay, so this will be nRT, natural log. Let's just keep the absolute value. We can use the log properties. If we're subtracting them, that becomes a division. Okay, so then that's our work done for an isothermal process. Okay, any questions on these 3 processes? Okay, then there was an extra bit asking why the 3 paths were unique. So remember, work done is a process function, and so I should have specified a path. However, for isochoric, isobaric, and isothermal, you don't need to specify a path. It's already implied. So why is that? Let's have a look. So why are the 3 paths already specified? Okay, well, let's have a look at all of them. Number 1 is isochoric. So remember, that means that the volume is constant. So if we look at our state space, that's where we do our integrals, PV. Okay, we're going to start off at some state, P1V. And we have to end at another state with the same volume because it's isochoric. So we have to end up somewhere here, P2V. Now, if we want to maintain that there's constant volume, there is one and only one path that can connect them, the straight line here. Okay, so just imagine that's a straight line. Okay, so we've got this one path that connects the two states such that it remains isochoric. Okay, so only one path, which is why we don't need to specify it. It's already implied if we say it's isochoric. Okay, what happens if it's isobaric? Isobaric, that means that P is constant. Okay, so again, let's look at our PV diagram, because that's where we do our integrals. PV. So if P is constant, let's say we start off here at P and V1. That's not P1, that's a comma. So that's P comma V1. And we need to end up somewhere here with the same pressure. The volume can be different, of course. Now, if we're going from the initial state to the final state, such that it's isobaric, again, there is one and only one path that can connect them, such that it's isobaric. If we don't care if it's isobaric or not, we can draw any squiggle from the first point to the second. But if it has to be isobaric, then there's only one path that does that. Okay, and then just by the way, the work done, remember we're integrating this, that's the area underneath this curve. Okay, and if we look at the vertical line, there's 0 area under the curve. So that means the work done is 0. Okay, here it's just the area of the rectangle. Okay, which we showed on the previous page. And number 3, if it's isothermal, that means T is constant. And we've discussed this already. The isotherms, those are the equation, the lines that satisfy P equals nRT over V. In other words, the hyperbolas. So what does that look like? Again, we look at our PV diagram. If we start here at P1, V1, and we end up over here at P2, V2, there is only one hyperbola that will connect these 2 points. So something like that. Okay, that is our isotherm. So if we want the curve to be isothermal, there's only one hyperbola that's going to do that. So the path is unique. Okay, so for these 3 processes, we don't need to specify the path because they are implied. Okay, for any other process, I need to give you the path. For example, if I just want you to calculate the total heat transferred, you know that that's a process function. I have to give you the path so that you can do that. Okay, any questions on this so far? Okay, so it's not too bad. Okay, so that was it for the homework exercises. Let's have a look at the tutorials. So last time I was asked to go through tutorial 2.5 and 2.10. So let's go through that. Sorry. Okay, I've got a question here about tutorial 2.5. Is there an initial high pressure or the pressure is the same throughout? That's the only question I have. Okay, yeah, so let's get to that. Okay, so for 2.5, we have the following system here. Okay, so we've got a box, or you can imagine it's a box with diathermal walls. Okay, so diathermal, no heat going through that. there's a leak in the box, so we just make a little hole, and the gas is coming out. Okay, like that. And the question says that this is an isothermal process. Okay, so inside the box, we have n moles of gas, and it's at a pressure P with volume V. Okay, so that gives you the macro state inside the box. The question also says that the gas is leaking with some pressure P naught. P naught, so that's the pressure going out. Okay, so if the gas is escaping, we can say that there are V prime, that's the volume of gas escaping after some time T, and let's say n prime moles of gas have escaped. Okay, so the question is, find the work done by the gas and show that it's equal to W is going to be P naught, N times V naught minus V. So P naught, that's the pressure, N is the number of moles, V naught is the molar gas volume. Molar gas volume. Okay, I don't know if you remember this from high school chemistry. The molar gas volume, we put a little m in the bottom there, that's V over N. What about the initial pressure? Yeah, I've put that here, P. That's the pressure inside the container. Okay, so we want to show this equation here. Okay, that's our goal, is to find the work done and show that it's equal to that. Okay, so there's a first couple things we need to do. Okay, so let's, I've already said here, we're going to have V prime be the volume of gas that escapes, N prime is the number of moles that escape. So let's N prime be the number of moles of gas that escapes. To fill a volume of V prime. So you can put a little measuring device at the end there if you want. After some time T, N prime moles of gas will have leaked out. If you collect that gas, it will fill some volume V prime. Okay, after some time. Okay, so N prime is going to be N minus N naught. Okay, so that's the difference in the moles. That's how much escapes. Okay, so how do we find the work done? So the work done by the gas while it's escaping is going to be the integral of P dV prime. Okay, so it's pushing out a volume V prime with a pressure P. In doing so, it does some work. Okay, so this is going to be the integral of P naught. That's the escape pressure. That's the pressure being used to fill up that volume V prime. So integral P naught dV prime. Okay, or you could just write dV, but I like the prime because it shows which system we're working with. Okay, so we want to integrate this. How do we integrate dV prime? Well, it's a bit difficult to keep track of how the volume is changing. It's a bit easier to work out how the number of moles is changing. Okay, so what do I mean by that? Well, look at the equation of state. Equation of state. So P naught V prime, so that's the equation of the state for the gas that's escaping at pressure P naught, it's filling a volume V prime, is going to be N prime RT. Okay, we can rearrange this to solve for V prime. So V prime is going to be N prime RT over P naught. Okay, all of those are constants except for N prime, that's changing over time. So dV prime is going to be RT over P naught dN prime. Okay, the number of moles is changing. N prime is changing. Okay, so you can think of this as like a U substitution. We're changing V prime to N prime. Okay, so what does the work done look like in this case? So the work done is the integral after our little change of variables will be from 0 to N prime. So in the beginning, 0 moles escaped. At the end, N prime moles escaped. So that's our bound for integration. We're integrating P naught dV prime. So it's going to be P naught. dV prime is RT over P naught dN prime. The P naught in the numerator and in the denominator, they can cancel. So this just gives us RT N prime, okay, after doing the integral. Now N prime, that was the number of moles that escaped. So this is going to be RT N minus N naught from our thing over here at the top. Okay, so let's multiply through by RT. So we're going to get nRT minus N naught RT. Okay, but that should look familiar. Remember your PV equals nRT. Okay, so this first one, nRT, that's going to be PV. N naught RT, that's going to be P naught V. Okay. Now, if we go back to what we wanted, the goal here, we had this P naught on the outside. So we need to factor out P naught. So let's do that. If we factor out P naught, we're going to get P naught, P over P naught times V minus V. Okay, good. Now, again, if we go back here, we wanted little v naught, which is the molar gas volume. So we need to find this molar gas volume for this first bit here. Okay, so how do we do that? Well, we know that PV is equal to nRT. That's for this P over here. So I'll put the yellow there. Then this P at the bottom here, that's going to be green. That's going to be P naught. V is N naught RT. Now we want P over P naught. So we can just divide the two equations and we get that P over P naught is equal to N over N naught. Okay, if we divide those. So we're going to get P naught N over N naught times V minus V. But remember, where did I say it? Here we go. Molar gas volume. This is the formula for it. It's the volume divided by the number of moles. So here, if we take the volume and we divide it by the number of moles, then that gives us the molar gas volume. So that's going to be P naught N times little v naught. So whenever we're dealing with molar quantities, we can use the little v naught. So the little, capital V for volume, little v for molar volume, minus V. And that's what we wanted to show. There we go. That's what was asked. So that is the work done. Okay, Any questions on that? Okay, everyone all right with that? Okay, then yesterday someone asked for 2.10. So let's go through that one. Okay, if you stuck with any of the other problems, just let me know as well, and we can look at those. Okay, so 2.10, that was with the rubber band being stretched. So tutorial 2.10. Okay, so we had a rubber band with a certain equation of states. So that just describes the states of the rubber band. So it was given by F is equal to AT L over L naught minus L naught over L squared. Okay, so it almost looks like Hooke's law for the force on a spring. Okay, but we've got a little extra factor here, just because it's not an ideal spring. Okay, there's a bit more complexity to it. Okay, but roughly Hooke's law for small expansions. Okay, so remember that was F equals KL. Okay, so we want to find the work done to stretch the rubber band. Okay, so find the work done to stretch the rubber band from L naught, so its initial length of 10 centimeters, to L equals 20 centimeters at 20 degrees Celsius. Okay, now none of these units are going to work for us. Centimeters, we don't care about that. We want it in meters, so that's 0.1 meters. 20 centimeters, that's not going to help us. It's 0.2 meters. And 20 degrees Celsius, we're not interested in Celsius. We want 293.15 Kelvin. Okay, so make sure that you're always working in the correct units. Okay, so we want to find the work done. Well, we've got the tension force F. If we want to know the work done, it's the amounts of energy we need to put in to overcome that force in stretching it from L naught to L. So W is going to be the integral from L naught to L of F dl. So force times displacement, that's the work done. If we do it over a total displacement, that's going to be the total work done. Okay, so that's going to be integral from L naught to L. F is AT L over L naught minus L naught over L squared dl. Okay, so we know that this is isothermal, so the temperature is a constant, so we can take that out. A is also a constant, L naught is a constant, so we can take those out as well. So it's going to be AT over L naught, integral from L naught to L of L dl, minus AT L naught squared, integral from L naught to L of L to the minus 2 dl. Okay, two simple integrals to do. So the first one, we can do AT over L naught. This is going to be 1/2 L squared from L naught to L minus AT L naught squared minus L to the minus 1 from L naught to L. Okay, so we just substitute the bounds, and we end up with AT over L naught. 2L naught, we can take the 2 out, L squared minus L naught squared. The minus and the minus, we can make that into a plus. AT L naught squared, 1 over L minus 1 over L naught. Okay, so you see this is quite similar to Hooke's law. Well, the first part is, because remember with Hooke's law, the potential is 1/2 k L squared. Sort of something here. We got the 1/2, we got the k L squared. However, there's this extra term plus this extra bit here, this extra bit there, and that's because of this extra term that we're adding to Hooke's law. Okay, so it's a bit more complicated than Hooke's law, but we see that this first bit makes sense. We've seen that before. Okay, so that's the work done. Now we just need to substitute in our values. So we're given AT, L naught, and L. So we just sub that in, and we get 0.38 joules. Okay, that's the work you need to do to stretch this rubber band. Okay, any questions on this one? Okay, anything else that you would like to go through? I think tutorial 1 and 2 wasn't too much to go through. Uh, 2.2. Okay, let's have a look at that one. Do I have that open here? Okay, let's have a look. 2.2. That wasn't part of the tutorial, but let's have a look. Okay, so for tutorial 2, it was only 3 and 5, but let's look at 2.2. Where's that? 2.2, okay. Okay, so we have an ideal gas undergoes the following reversible cycle. An isobaric expansion from P1V1 to P2V2, followed by an isochoric reduction in pressure, okay, an isobaric reduction in volume, and an isochoric increase. I wanted to confirm if PF minus PI, VF minus VI is valid. Where did you get that formula from? I haven't seen that before. Where's that from? Online. No, I've never seen that before. Which kind of process is that for? Did they say if it was isothermal or isobaric or anything? For the entire work done? No. So if you want to find the entire work done, you need to do those integrals along each part. So if I just draw a little bit here, let's say here, okay, let me just sketch it in here. So we've got P and V. So the first bit is an isobaric expansion. So that means that the pressure is constant. So it looks something like this. Okay, the next bit is an isochoric reduction in pressure. So it looks something like that. Okay, and then an isobaric reduction in volume. So that looks something like that. Okay, and then an isochoric increase in pressure. So that looks something like that. Okay, so what we want to do, if you want to find the network done, that is this bit in here. Okay, so the question that you had with that PV thing, that's right, but you need to know that that's only for these processes here. So if I just go, let's pick another color here. So that if this is PR and this is PF, and this is, oh, sorry. Yeah, PR over there, PF over there, VR and VF, then yes, for this specific case, then that does work because the area is equal to delta P times delta V. Okay, because where delta P is this length over here, let's put that in pink. That's our delta P. And let's put this in green. That's our delta V. So it's only for this sort of picture where you can use that formula. Yeah, if you want to do the integral, you would get exactly the same answer. So the integral along the first line would just be the P delta V. And then along the vertical lines, it's going to be 0. And then you can do along the bottom line as well, along this bottom line here. And then you'll get the same answer.
So for the integral, what if you use minus P delta V?
Yeah, you can do that as well. But remember what that minus sign means. Are you working out the work done by the gas, or are you working out the work done by you? So you need to be careful on what you mean with that minus sign. So if you want to do the work done by the gas, so just how much work is done by the gas, how much energy is leaving the gas, then you don't put the minus sign. If you want to know how much net work is transferred, then you put the minus sign, and then that means minus however amount is leaving the system. So just remember what that minus means. I've got a question here. So again, that isn't valid for other cases. Yes, that's right. So that formula over there is only valid for square or rectangular cycles. So just make a little note here. This is only for rectangular cycles. You can't use that in general. Okay, and that bit about the minus sign, is that you okay with that?
Not so much. Not so much.
Okay. Okay, no worries. Let's go back to the OneNote, then we can have a look. Okay, so basically what that minus sign is,